Good morning, students. I hope you guys are well prepared for today's quiz because it's going to be a little bit more difficult than the usual quizzes we have. So in order to maybe improve a little bit your grades, like you have the opportunity to ask as many questions as you want during the next 5 minutes, or we can just go through the lectures again and revise them together. I guess if you guys don't have any questions, we can revise lecture. So in the object detection lecture, we spoke about two main models, which are the RCNN family and the YOLO family. But before we started that, we described a little bit what is object detection, what are its application areas, and then we spoke about the most basic model for object detection, which is the sliding 2D CNN. We saw that it suffers a lot from speed constraints, and we proposed this pyramid idea of improving the speed. We also saw that there is another method that is based on machine learning completely, it doesn't require any training, and called selective search, which proposes to us different regions of interest that could be or could contain objects. We saw that the best way or the easiest way to evaluate the performance of an object detector is to use the intersection over the union. The higher the intersection, the better, and the lower the union, the better. We saw that, of course, this easy model suffers a lot from the non-maximum, suffers a lot from crowding. And the best solution to fix that is using non-maximum suppression. Simply, we take the largest or the most confident prediction at every single location, right? And we use that by checking the intersection over union and if it's greater than a certain threshold. We saw that the first model proposed for object detection in our lecture is called RCNN, or region-based convolutional neural networks. And simply, they just use the selective search algorithm, and then they forward every single one of these regions into the CNN for classification by using, of course, selective search. We saw that this is a very slow training process and a very, very slow inference process, and that selective search is not dataset specific, which leads to lower performances. The next model we spoke about is the fast RCNN model, and it removes one small constraint or removes one problem from the RCNN architecture, which is the time problem. In this case, instead of sending every single region proposed by the selective search algorithm through the CNN, we just send the image once through the CNN and find the corresponding area of this region of interest inside the convolutional feature map, just through this calculation mapping. We saw that this is an amazing improvement in terms of speed, so it's 10 times faster than RCNN, but we still have the same reason of problem, which is the selective search algorithm that takes up to, let's say, 10% of the time of the inference. And of course, any improvements on the model should be an improvement on the selective search algorithm. And this is what Faster RCNN did. Faster RCNN proposed a region proposal network very similar to what we have proposed in the start of the lecture. And this region proposal network will be just sliding a set of classifiers or a set of anchors with different shapes and sizes or ratios throughout the convolutional feature map, and tries to predict whether this area belongs to an object or not. So as we can see, we have 2 times k. K is just the number of boxes, so 2 times 9 in general. So we have 2 times 9 scores for prediction, which is it an object or not? And of course, we have the 4k coordinates, which are the x, y, and width and height, for example. And this gives us the faster RCNN architecture. And then Detectron, as we've seen, is just a good library provided from Facebook that implements majority of these algorithms for computer vision. And then, of course, we spoke about YOLO. So here, for example, we saw that it's just a couple of convolutional layers, which end up with a convolutional feature map that contains 3 boxes. Each box will contain a prediction for the class, objectness score, whether there is an object here or not, and of course the coordinates of that object. We usually have 3 boxes in this score, in the number of channels of that feature map, and these boxes correlate to different anchor ratios. And the different anchor sizes, so this at every single scale we have different anchor ratios, but the different anchor sizes come from the different scales of the feature maps. So this scale is useful for detecting the smallest or the largest objects. This one is used for detecting the medium objects, and this one is used for detecting the smallest of objects. In the GANs lecture, we spoke about GANs in general. We said that GANs are pretty useful for the generation part, and that they do not model this P of data because it's pretty difficult, and that makes them much easier to train than other neural networks which tend to explicitly model the probability of the data, probability distribution of the data. We saw that there are 2 main components of the GANs. So there's the discriminator and the generator. We saw that the generator is, of course, trying to generate images based or starting from an input of random distribution, or could be some sort of a prior that we control. And of course, the discriminator was just a basic classification network. We saw that the goal is to reach the Nash equilibrium instead of going for convergence of training. And we saw that it's pretty difficult to detect the Nash equilibrium. The loss function of the GANs is pretty easy, so we are trying to minimize with regards to the generator and maximize with regards to the discriminator the mean value over the data for log of d of x plus the mean value over the priors for log of 1 minus d of g of z. So d of x is the discriminator over real images, and 1 minus or d of g of z is, of course, the discriminator over the fake values or fake images. So the goal of the discriminator is to fool, or the opposite, the goal of the generator is to fool the discriminator and generate images that look as realistic as possible. And we saw that the way of training is usually split into 2 parts. So first we train the discriminator, and then we train the generator, and we repeat. And in order to do that, we usually freeze the layers of a certain of the module that we are not training. Of course, there could be different loss functions, and there is a trick. For example, for this case, where the loss function that we use by default is too flat in the area of close to 0. So we kind of could replace it with a similar looking error function, but that is more curvy around the 0 area. Curvy means that there is a bigger change in values or in intensities in this area, leading to a much faster training. And of course, there are two major problems with training GANs, which is the non-convergence and mode collapse. And of course, for mode collapse specifically, it's trying to generate the same image again and again, which is technically a correct thing to do. So generating like one image from the training data would lead to a perfect score on the loss function. And then we saw that the simple solution would be to create different generators and improve the feedback that the discriminator is giving. Instead of saying just this is a fake image, we say this is a fake image coming from that generator, leading the generator to forcing the generator to generate different styles of images such that the discriminator doesn't remember his work. Of course. Now, there are other simple solutions, for example, scaling the pixel values between -1 and 1, avoiding max pooling and using a convolutional stride instead, using Adam optimizer and others. And of course, I gave you some reading to do at home in order to basically solve the questions in the quiz. Does anybody have any questions so far? Okay, very nice. If there are no questions, then I think we can start the quiz. As I said, the quiz might be a little bit more difficult than usual, but it's pretty easy, and just try to solve it as fast as possible. So let me edit the settings. The timing. Today is 22. Okay. Let's open it at 42. Close it at 55, let's say. Enable time 10 minutes to check everyone. Okay, can you guys see the quiz right now? It's called quiz number 3.
Yeah.
Can you enter? Does it give you the questions yet?
Right now it does.
Good. Good luck, guys. And if you have any questions or clarifications, please ask me. I hope the majority of you are close to finishing, so please, you have 1 more minute left. Try your best to submit the grade to finish the questions, right? I think the quiz is closed right now. Nice. Let's take a look at how well did you guys do. From what I'm seeing, that's kind of good, right? So we have a couple of, let's say, A's. A majority of you are around the B area and a couple of C. But we also have, let's say, we have 4 students who got D. That's a bit bad. Please try to, revise or ask as many questions at least during the revision session. Do you guys want me to go through the quiz's answers or just give you the results? Just give you your grades?
Can we do both?
Maybe we first see the results and then we'll ask questions if we don't understand the right answer.
Хорошо, of course. 1, 2. I assume that you guys can now see your grades, I hope. So, did you guys see the results? If you can't see them, probably I did something wrong from my side. It looks like I should give you the grades.
Yes, we see.
Okay, good, nice.
Like first task, the task of classification is done not by RNN, right, but with in our network.
RCNN.
Yeah, like if we check the scheme of RCNN, like here, no, like the picture, we will see that the bounding box task done by one network and the classification task done by another network. No?
Let's take a look at it. So you see, this is the RCNN, right? All of this is the RCNN network. So for example, if I say, same thing, if I say, is the task of generation done by the GAN? So GAN is not just one network. So GAN is all of the neural network, the generator plus the discriminator, right? So RCNN is all of this, including selective search. And here we can see that it's the same network that does the classification and the bounding box regression. Of course, the classification is being done in this case with an SVM and the final layer, but the SVM's calculation are kind of being warped into a neural network's calculation. So it's the same thing as what you already know. So for example, here, probably this is the image that confused you. This is the same neural network, all of this. Right?
Yeah, okay, understood.
Nice. So probably, yeah.
SVMs are like not pre-trained and that training within the network, right?
Can you repeat the question?
SVMs, those we use to classify, they are not pre-trained and they are just for the trained during our process of training the whole.
Exactly. Yes. Yes.
Okay.
So it's just instead of using condition like previous errors of what is it called, normal neural networks, now you're using the error of an SVM, right? So it's still a differentiable error and it goes through the convolutional layers normally. And for them, this loss gave better results than the traditional cross entropy loss. But they soon abandoned this idea of using SVMs. Nice.
Could I also ask a question about the stopping question?
That's okay. That's okay. We will go through all of them together, right? Let's just take a look at them. Right?
Okay.
The region proposal step in RCNN uses ROI pooling with selective search. Is this true or false? Simple question. When did we introduce ROI pooling? Certainly not at the RCNN.
RCNN. It's
Very
false
well.
for the simple RCNN.
Exactly. So the questions are pretty easy, right? If you have followed during the lecture, you shouldn't have any problem. Fast RCNN uses selective search to find 2,000 proposals. How are these proposals later classified? We pass each region through the CNN and classify them, or we send them through the region proposal network, or we find their mapped regions inside the feature map and extract the feature map extracted by the CNN. So which one of these? Very easy question. Very direct result. I just said it during the revision, right? During the revision, I just
Yeah, it's clear that further we go through the CNN and extract the features that were selected previously, but the question is kind of unclear because the later classified. Maybe you can say next time later manipulated, something like this, because just
let's
going
take a
through
look.
CNN is not classification.
Gotcha. So let's take a look at it. Is this answer remotely correct? Of course, it's not, because region proposal networks were not invented in the time of fast RCNN, right? So this answer is absurd. Now, the second answer is we pass each region through the CNN. As we have described, the only change in fast RCNN is that we do not pass each region through the CNN, right? So this is the only thing that was added in fast RCNN. So if you remember, like the only difference between RCNN and fast RCNN is that we do not pass each region through the CNN. We pass the image once. This is the only thing different, or the only new thing that was introduced in fast RCNN. So this is wrong. This is certainly wrong. And this is saying we find their mapped regions inside the feature map. Looks like correct, right? Let's see. ROI pooling must always receive. This was a bit confusing, not confusing, but let's say it was a trick question, right? ROI pooling must always receive the same size of input. Now you can stop right here. Does ROI pooling always receive the same size of input?
No.
False. If you want to continue, just like max pooling. So first thing, ROI pooling is not like max pooling. So they're completely different. Like they're different concepts, right? So they have different names, they have different processes, but it uses faster algorithm to do the calculations. I just added this to like confuse you guys a bit further, but I hope it didn't work. So certainly false, because again, just the first part of it is completely wrong. ROI pooling takes the maximum of a region in the input map and maps it to a single pixel. And the output similar to max pooling. ROI pooling also has a fixed size kernel that passes through the image as max pooling does. Again, a very clear question to be wrong because ROI pooling does not have a kernel. So it does not have any kernel, and it does not have, certainly does not have a fixed size kernel, right? So false. Hello, sorry, my internet is very breaky these days. So if you guys see that I disappeared, that would be a problem. So faster RCNN still uses the selective search algorithm, but doesn't send each region through the CNN. This is just like very easy question to make sure that you guys can differentiate between fast RCNN and faster RCNN. So is this correct or false? As we said, probably during the lecture, in here, faster RCNN does not use selective search, but uses region proposal network. So this is, again, the only thing that changed in faster RCNN. So faster RCNN, if we come here, no region proposal algorithm, we have a region proposal network. So it's false. The majority of them are false. Faster RCNN provides the regions of interest by using, okay, this one could be a bit tricky, right? So we know that faster RCNN provides the regions of interest by using RPN, as we have seen before. But I didn't want to put the word RPN because anybody who just come to the lecture and see the word RPN here or here would be able to answer the question correctly. So I just added deep learning. So again, RPN is a neural network. So deep learning is the correct answer. Selective search, completely wrong. Greedy algorithm is selective search, so also completely wrong. SVM classifier is absurd, right? So if you answered SVM classifier, that's a very, very wrong answer. So the only correct answer is deep learning, and it is the correct answer. RPN finds the location of objects by sliding K anchors on the convolutional feature map, the input image, or selective search. So again, very absurd answer, selective search does not exist. Now, two very confusing answers are the convolutional feature map or the input image. So what do you guys think?
Convolutional feature map.
Precisely. If you come here, you see that we are working on the convolutional feature map. We do not. So this one, I was like, I put this question just to make sure that you did not confuse this with sliding through the image, because in reality, we are sliding in this point, and this is just visualization of the area we are touching when we are working in this point. But that's a very good question. A very good answer. YOLO also follows the same pattern of proposing the regions of interest and then classifying them. Also, this was like a very basic question. YOLO means you only look once, hence the rest of this answer is absurd, right? So false. Does the generator part of the GANs update its weight based on the loss influenced by the training data? This was a bit of a tricky question, right? I'm sure you could easily just like training. You should like just yeah, robust to overfitting since the generator never sees the training data. And this is like the question in here. We did this, we spent some time on this, explaining this during the lecture. So I wanted to ask a question about it. But it's pretty easy, right? So we clearly see from the architecture that the training data is only going through the discriminator and the generator is here, never ever interacting with the training data. So it does not come here. It only goes to the discriminator, and the generator sends stuff to the discriminator. But never there is a connection between the training data and the generator. So this is false, sorry. Next is early stopping. Okay, this was part of the reading that I gave you yesterday, but it's also something that we spoke about yesterday. So early stopping is very useful for training neural networks. This is a correct statement in general, and especially for GANs. This is very wrong statement. As we said, GANs tend to do the following, right? So the loss functions are always going like this. So if you do early stopping, you're going to stop here, right? Early stopping is going to stop you here, and you will not continue the training, because usually it does this, but like with time, it decreases like this. If you stop here, you're never going to finish the training of GANs. And this is why early stopping is bad for GANs.
Could I ask you? On the lecture, you said that training the GAN, we need to find the Nash equilibrium when the loss of the discriminator will be 1/2. So if for several training epoch we gained a 1.5 loss of the discriminator, how we can stop otherwise without using any early stopping? Like early stopping is just not stopping in the earlier stage, it's just stopping after the loss is repeated on the several stages. So we see that there is no reason to continue learning.
As you can see in here, the loss is being repeated multiple times, right? But we do not stop, we continue. So if you read like the part that I gave you, and we explained this during the lecture. Oh, sadly, it's let's open Private Navigator. Let's go through it together. But which one is it? This one, right? Yeah. So if you come here, you'll see early stopping. What does it say? Another frequent mistake you may encounter in GANs is GANs training is stop the training as soon as the generator or the discriminator loss increasing or decreasing abruptly. Only later, he's going to start speaking about his life. So often the losses go up and down almost randomly, and there is nothing wrong with that. I achieved some great realistic results while the generator loss was way higher than the discriminator loss, which is perfectly normal. Now let's explain the intuition behind that. We are working in a situation where two neural networks are forcing or facing each other and trying to fool each other. So at a certain stage, or like during the training, one of them is going to get smarter than the other. So the results of this one are going to go, or the loss of this one is going to get higher, and the loss of that one is going to get lower. And they will keep on iterating over this pattern again and again and again and again and again until they reach this Nash equilibrium. As we said, there is no guarantee of the Nash equilibrium. There is no mathematical way of finding the Nash equilibrium, but we can detect that, or we can get an intuition about it when we see that the accuracy of the discriminator is about a random classifier, or 1 divided by 2. But we discussed that 1 divided by 2 is not an obligation, because by default, we should get 1 divided by 2 during the early stages of the training, and that is not an indication of Nash equilibrium. Nash equilibrium happens by the end of the training. Is that more clear?
Yes.
Nice. And how to set the learning rates for this was this was easy technically, but I added a couple of explanations which could have made it a bit more difficult to get. So, but the answer should be direct, right? So if you read this article, this answer should be copy-paste. Same values for both of them to get more balanced training and fight against non-convergence. This is just absurd. I was just playing around. Generalizing or generator learning rate is higher than the discriminator because the generation is harder than discrimination. Again, pretty absurd. And the last one is discrimination learning rate is higher than the learning rate of the generation to fight against mode collapse. And this is what you're going to find inside this article, very clear. You will find it in 3 different tips, right? So this is like the most important tip inside the whole article, which is the 2 times update rule or something like that, T2UR. And that's it. Yeah, this is the question. Of course, it might have been a bit confusing because I added these this explanation for these 2, but for this one, it's pretty clear that it's the correct answer if you read the article again. So was the quiz a bit harder this time? From the grades distribution, the quiz was quite average, right? So majority got a B, but there were 3 students or more who got an A. And yeah, also another majority got a C. And sadly, 4 students got a D, and that was very bad. I hope the thing was clear, or the lecture was clear, or the quiz was easy for the majority of the people who attended the lectures. If there were some difficulties, please do revise. Please try to stay up to date with the course. The content is going to get very difficult, especially the next lecture. So the next lecture, I highly recommend that everybody stays till the end. So I can see that the majority of you guys have already left. But please, for the next lecture, try to stay till the end. It's going to contain a lot of math. And if you do not do it with me during the lecture, it's going to be very difficult to get this math outside. So even if you are going to study it like on YouTube or something like that, the math part is not going to be introduced. So the concepts and content might be found outside, but the math part is certainly not going to be explained as it would be during the lecture. So please do attend. For the next few lectures, things are going to be a bit more difficult than usual. But for today's lecture, it's going to be very basic. Today's lecture is the last lecture or the last basic lecture that we will have, and it's about facial detection and facial recognition. So the contents of this lecture, do you guys need a break, or can we go directly and start? If any of you need to take like a small break and take some coffee to come back and be more energized, please interrupt me at any time. So the content of this lecture would be about, like this, about computer vision terminology for human faces. Then we'll speak about the facial detection algorithm called Viola-Jones algorithm. You will find it's pretty used everywhere right now. So till recently, it was being used for like iPhones and stuff, and till now it's still being used for Snapchat and all of these what are they called, TikTok and all of that, the things that use facial recognition to perform games on your face. And of course, the last part is facial recognition using eigenfaces. Very basic idea. Today's focus is going to be on facial recognition and facial detection. Usually there are 4 tasks that you could do with human faces. The first part is to detect the human faces. Of course, human face detection does not mean that you will understand who the person is. You will just detect the face. So this is the face, this is the body. You will do object detection on the face. Of course, you can treat this problem as an object detection problem and train, for example, a YOLO V4 for YOLO v5 to do the facial detection part, but there are other techniques which are kind of faster during inference, but slower during training. So if you do not have a GPU, or if you do not have a lot of RAM, then instead of using YOLO and stuff like that, you could use the algorithms we will speak about today. Facial recognition is about linking basically the face that we found into a concept or into a person that we have in our data set. Pretty widely used for many things such as opening your phone and stuff like that. Facial analysis is about understanding the contents of the face, right? So basically, let's say he has green eyes, the age, for example, the nose, the teeth, and stuff like that, analyzing these concepts. Facial tracking is basically you have a face in here and you're tracking where the face is moving inside a video. The facial detection is like the, let's say, the thing that you would be doing most often in industry, followed by facial recognition. These two, they're not very important for us, at least for today. So facial detection is available in most digital cameras nowadays. So basically they just try to focus on your face. Some of the challenges is a picture may have 0 or 1 or many faces, and faces are not the same with spectrals, mustache, etc. And sizes of the faces can vary a lot. So the simple method is to slide a window across the image and detect the faces. Too slow, pictures have too many pixels, you see? But again, as we said, you can easily train YOLO to do that. So right now we're going for an easy algorithm. So as we said, the basic idea is to slide a window across the image and evaluate the face model at every location. A good face model should contain 2 main characteristics. So the first one is a high detection rate. So the total number of faces that are correctly detected divided by the total number of faces that exist in the image or in the picture. And it should be a very high number, right? So let's say there are 1, 2, 3, 4, 5, 6, 7, 8. We should try to detect as many of these 9 faces as possible. This is the detection rate. False positive rate is that we should not be detecting faces when they don't exist. So detecting a face when the face does not exist is called a false positive. And we should try to reduce this as much as possible. So a good system should have a high detection rate and a low false positive rate. This is what a false positive looks like, right? So false positive, again, falsely predicted as a positive. And you can easily interpret it once you see it like that. These two guys invented the Viola-Jones algorithm. So this is Viola and this is Jones. And the algorithm is honestly one of the most famous algorithms in the field of computer vision for facial recognition. And it's, as we said, it's still being used. It's a very basic algorithm, very simple idea, but it's pretty powerful, at least in terms of results. It's a very famous method, and it's characterized by a very, very slow training process, but a very fast recognition process. And this is good, right? So the inference is fast, the training is slow. Training is slow, it's not a big problem because like big companies can do it locally at their machines. It can take up to 1 year. They do not care, right? So because they will prepare it for the new version of the iPhone, for example. And what they really care about is this fast recognition part and accurate recognition. So the key steps is to compute this integral image for fast feature extraction. This is just a trick to speed up, again, the research, to speed up the calculations. Use boosting for feature selection. Now I'm going to stop and ask you a question about the course from Professor Khan. Did you guys study boosting? Add a boost. Please tell me you did, because if you didn't, this lecture is going to be hell. How to combine different, yes, go ahead.
A little bit, but like only gradient boosted decision trees, but we touched it after the final exam, so nobody really checked it.
You're telling me you didn't study ensemble models?
We kind of studied random forest classifier.
Yeah, random forest classifier. No, you didn't study AdaBoost.
Briefly, maybe.
Oh, this is weird. This is very weird. Professor Khan has a full lecture about AdaBoost, so it should not be the case.
But the full lecture for data science masters, but the bachelor have merged lectures for all of the tracks.
Oh, okay, that's gonna be a big problem. Well, that's okay. So boosting is a technique to combine basically weak learners. Weak learners is about combining weak classifiers, right? So as you said, for example, for random forests, what you're going to do is you will combine different decision trees. These decision trees alone are weak learners or weak classifiers, but if we combine them together, we would get something much stronger. And of course, the last part is the attentional cascade. And this is just to fix a problem with high, the problem of high false positive rate. So we will speak about that. Before going there, we will speak about something called as Haar-like features. So Haar-like features comes from this guy who is called Alfred Haar, who created these features. They're very basic features. As you can see, these are some kernels that are useful for different edge detection cases or different detection of different features. So here, for example, when you have white areas here and darker areas here, and these features are very simple features that can be used to detect different concepts. So for example, here you are detecting edges, here you are detecting lines, and here you are detecting this for rectangular features. So why is this pretty interesting? So for example, for this one, it could be put, we could put it on the eyes region. Why? Because usually this area is whiter than the eyes area, right? You see this? Same thing, for example, in here. For the nose, for example, we usually have this line. So there tends to be a very good separation here. And this can be detected using a simple edge feature. So what he did is use all of the potential combinations of these features, right? And then, of course, if every single one of these features is alone not enough to detect the face, so these are what we call as weak learners, and then he combines them using the AdaBoost method. So the content of the lecture is going to be a bit disoriented since you guys don't know what AdaBoost is. But I'm going to try my best to explain the lecture and explain basically what AdaBoost is separately, or what AdaBoost does. So what do these features have to do with the faces, right? So as we said, these edge faces can be, or the eyes regions tend to be darker than the cheeks region. The nose region is brighter than the eyes region, and all of these other explanations that explain why these very simple and basic what are they called, features or very basic kernels can be used to detect concepts in the face. Same thing as you guys can see here, right? The nose, the eyes. So the feature calculation, to obtain these features, what we simply do is we take each one of these 5 rectangular areas and we subtract the sum of pixels under the white region from the sum of pixels under the black region. So let's say if this area is very darker, is much darker, then it's going to have values like 0. And this area is much whiter, then it's going to have values like 255. If you subtract the sum of white regions, 255, minus the sum of black regions, you're going to have a very high number. If you have a very high number, this means this feature has been detected. If it's a low number, this feature is not detected. So as we can see in here, if you reduce, you do the minus between the sum of the white area with the black area, you're not going to find a very large threshold or a large value that passes the threshold. But if you do on the pixels of the eyes and the pixels of the cheeks, you're going to find these values passing a certain threshold. So this is a face, the area, the eye area, shaded area is dark, the nose area, white area is bright. So F is large enough, hence this is a face, right? How will you calculate this, guys? It should be simple, right? So this minus this. Pretty easy, right? Integral, yes. So this calculation is a bit difficult, right? So this is not a bit difficult, but it's a lot of calculations at every single pixel, at every single scale, right? So for example, here we have this size of the feature. Of course, we could shrink this window a little bit more, and we will have a different calculation. Shrink it even more, and we will have a different calculation. And if we put it on a different pixel, again, a different calculation. And again, at every single pixel, we have 5 different features to compute. So it's a lot. One very simple trick that can speed up this calculation is to prepare for it, right? So we're going to prepare the sum before we get there. And this is called the integral image. What we simply do is the integral image is the sum of all pixel values above and to the left of xy, right? So for example, the first pixel in here, there is nothing above it or to the left of it. So this value will be only itself, right? But for this second pixel is going to be this pixel plus this pixel. If we go here, this pixel, there's nothing to its left, but there is something above it. So it's going to be the sum of this plus this. And this pixel is going to be like, has pixels on its left and pixels on its above, meaning it's going to be this plus this plus this plus this. Same thing, for example, for a pixel in here, it's going to be the sum of all the values in here. So let's take a look at it, right? This pixel, all of these. So this is what it should look like. 1 stays the same, 2 becomes 2 plus 1, 5 becomes 5 plus 2 plus 1, 7 becomes 1 plus 2 plus 5 plus 7. Of course, you don't have to do this calculation again and again. Only thing you can do is while you are building this, you can increase it, right? So this is 1, you put it here, 2 becomes 2 plus this value, 5 becomes 5 plus this previous value, 7 becomes 7 plus 8, 2 becomes 2 plus 15, and so on and so forth, until you finish the integral image. So this integral image kind of gives you the sum of everything before this pixel, right? So you kind of already prepared the sum. Doesn't matter if you're going to do the sum of this region or this region, you already have the sum. This sum would help us, calculate. So let's say the sum of pixels within the rectangle D can be computed with 4 areas of references, right? So this is D, this is what we're trying to compute. But if we have the integral image, that means at this point, at this pixel, we have the area here. At this pixel, we have the area here, or this area here. At this pixel, we have this area here. And at this pixel, we have the whole region. So if we have these 4 points and these 4 values, calculating D should be a very simple, calculation, right? So basically, what we do have is the value of the integral image at location 1 is the sum of pixels A, the value of location at 2 is A plus B, the location 3 is A plus C, and of course the location at 4 is A plus B plus D. Now, if you have this sum and you have the values at 2, 4, and all of that, you have all of these values, you're just looking for D, it becomes a very simple equation that you can calculate, right? This is what the integral kind of gives you, right? So the sum within D can be computed as 1 plus 4 minus 3 plus 2. And this one gives you the following. So if you want to calculate the sum at this region, instead of going through the image, all of it again and again, only thing you have to do, go to the integral image and make one simple calculation. So going from like O of n m into just O of 1. So this is the use of integral image in Viola-Jones algorithm. You go from O of n times m into O of 1 algorithm. Of course, O of 1 plus O of n plus m. So it's much faster. You may consider these features as, why do we need, of course, why do we need to find pixel of some algorithms? You may consider this when you are calculating these different values. So again, as we said, the sum of the white area minus the sum of the darker area. So if you're going to calculate all of these features, you're definitely going to need this sum. And since they can be of different sizes and different aspect ratios, instead of repeating the sum at every single aspect ratio, repeating the sum at every single pixel, now you are repeating only this simple operation at every single pixel. So it's still a lot of calculations, but it's much faster calculation. There are five basic types of features, which we have been seeing from the start. So there is this type 1, type 2 for rectangular, for edges, either horizontal edges or vertical edges. We have type 3 and type 4, which are for lines, and this is for these like areas where we have whiter here and darker on the edges. Each basic type can have different sizes and different aspect ratios, as we said, and the following feature windows are the same type too, even if they have the same different sizes or different aspect ratios. So different sizes means big, or like more on the flatter area, or here more on the thinner area. So this is what aspect ratio is. Similar to what we were seeing in anchors before. Nice. Since faces can be of any size, so an example, face can be big or small, ranging from 24 to 20 by 24 pixels, or like if you're in a selfie to 1024 to 1024. So there are faces within different sizes of the image. So we need feature windows with different sizes, as we described before. Now, the training of Viola-Jones algorithm, which is the thing that takes the most time, simply we give it a lot of face images. We give it a lot of non-face images like this, and he will try to build a classifier using this one. So there's a very simple problem. When you are building with all of these features, of course, all of their combinations, so we have 5 multiplied by a very large number of ratios, multiplied by a very large number of, what are they called? Sizes, let's say that. You get a very large number and you can no longer like compute it efficiently, right? So even though each feature can be computed very efficiently, computing the complete set is prohibitively extensive, right? So Viola and Jones found a small trick that small numbers of these features can be combined to form an effective classifier. And this is the goal of using ADA boosting or boosting methods or ensemble methods in general, which is weird that you guys don't study boosting and bagging. That's okay. So the main challenge was to find these weak features that can be combined into an effective classifier. So we have 1,000 or 160,000 features, which is a very large set. The solution is to select good features to make it more efficient using boosting. Boosting is a very simple technique. So it's a classification schema that works by combining weak learners into more accurate ensemble classifier. So we take weak learners, such as, let's say, SVM, and we combine it with other SVMs, and they will form a much stronger learner. So a weak learner is a classifier with accuracy that can be enhanced, right? So it's only slightly better than a chance. And we can define weak learners based on rectangle features, and training is definitely needed. So the training of boosting is pretty simple. We take the training data, we learn a classifier, and then the prediction is basically the sign of this classification. If it's positive, then it's positive. If it's a negative prediction, then it's a negative prediction. Pretty simple. Boosting, so train next classifier by focusing more on the harder points. So what we simply do, we have our beautiful classifier. We go to the classifier and find its misclassifications. Nice. So once we find these misclassifications, we increase the weight. Remember, I'm sure you have seen what weighted classifiers are, right? So a weighted classifier is a classifier that has a weight for every single sample. This weight can influence the loss function for that specific sample to be much larger than the others. Hence, the overall learning will focus on getting that sample correct. So the first one will learn everything in the same way. The mistakes of that one, we will focus more on it once we are training for the next one. And then, of course, this will be repeated again and again and again and again for all of our learners, for all of our weak learners. So it's a very sequential process, right? We train one, and then we train the next one on the mistakes of the first one. Then we train the second one on the mistakes of the first and the second. We train the third one on the mistakes of the first and second. We train the fourth one on the mistakes of third, second, and first. This allows us to build much stronger classifier, which is the combination of all of these weaker classifiers. So the AdaBoost training, for example, with like 5,000 faces and 9,000 non-faces, use AdaBoost for training to build a strong classifier, pick a suitable set of features of different scales and positions, and pick the best few. This training can take months to do. And of course, as we said, if it's going to be used for like a big company, it can take even years to train. The testing, though, is much faster, right? So we scan through the image anywhere, pick any window of size, any size bigger than 24 by 24, rescale it to size 24 by 24, pass it through the strong classifier for detection, which is just a combination of these weak classifier, report a face if there is any positive outcome. Boosting for face detection. So the paper, it shows that the following two features obtained after training in cascaded, picked up AdaBoost have 100 detection rates and 50 false positive rate, meaning only these two features were useful enough to have all the faces detected, but one small problem, false positive rate is very low, right? Or very high, let's say. So the false positive rate is very high. You have a lot of these rectangles everywhere around the image. But the good part is only two features gave us this very good detection rate, but it has a very high false positive. So what they decided to do is this attentional cascade. It's a very basic decision, which is Instead of using only 2, we can build like 50, let's say. So let's come here and build like 50 proposals. And what we do, if the first model or the first classifier with only one feature rejects it, if it tells us this is not a face, we reject this part, or we reject this window and say it's not a face. We move on. If it tells us it is a face, then we doubt, right? We confirm with a more complicated model, and this complicated model has more features. If it tells us it's not a face, we confirm it's not a face and we stop. If it tells us it is a face, we kind of doubt it a little bit and we go to a more complicated model. So this is the cascade that you can see, right? At any step, if any one of these models tells us, no, this is not a face, then no, it is not a face, we reject it. So let's come back. For example, here, 2 features, only this and this one. It tells us it's not a face, then clearly we say it's not a face, right? Because it has a 100% detection rate. So if it says it's not a face, we ignore it and we move on. If it tells us it is a face, we doubt it because it has a high false positive rate, and we move on to a more complicated model. This complicated model now has 10 features. Again, we trust it if it says it's false, but we don't trust it if it says it's 50, if it says it's true, and we repeat this process again and again until we finish, until we reach the maximum level number of features that we can use. If it tells us, if they all agree that it's a face, then we say a face is found. And this reduced drastically the false positive rates. We have 15 minutes. Now we can finish the lecture if you tell me one thing. Have you guys already studied PCA well?
We studied it. It was like half of lecture, but I'm not sure if everybody remember it well.
Yeah. So this part is going to be pretty easy if you remember PCA. It's going to be pretty difficult if you forgot PCA.
So we
So
know
now,
the essence, what does the algorithm doing, and that it use eigenvalues. But...
That's nice. That's nice. If you remember what eigenvalues are, that's good. So the algorithm is called eigenfaces, and what it's trying to do is basically represent a face in some sort of a PCA space, and then from there we try to find the closest space possible in there. So facial recognition, the objective, so what it is, we learn about eigenfaces, and then we learn how they can be used for facial recognition. So facial recognition is the challenge of classifying whose face is in an input image. So we're not detecting the location of the face. We detected the location of the face. Now we're trying to understand who is this person. This is much different than face detection, where the challenge is to determine if there is a face in the input image or not, and where it is, of course. With face recognition, we need an existing database of faces and, of course, their names. Given a new image of a face, we need to report the person's name. This is pretty useful for many applications, such as criminal identification, identity verification, patient monitoring, and etc. So what it's trying to do is try to learn some features about the image or about the face that are discriminating, right? So we're trying to learn as many important features as possible. So what we do is we take an image of a face, we flatten it like this, it becomes a face vector. But instead of using a face vector like this, we're going to map it into PCA space. What is very important about PCA is that the first few, what are they called? The first few components are the most variant informant, right? So they contain the biggest difference between the faces. So basically what we are doing is we are mapping a face from this 1D vector into a space where the faces are much different from each other, leading to, if we get a new face of, let's say, Bush, its location in the mapped area would be closer to the faces of Bush, but very far from the faces of other people. Why should we not just use a pixel by pixel comparison? It's because we don't know which pixels are more important than the others, right? So this is the problem of facial recognition. We can solve this problem by using PCA, which will give us the set of components or combination of pixels that are the most important. So eigenfix, the eigenfix approach is that images are points in a vector space. Use PCA to reduce the dimensionality and keep only the components which contain the largest variation in the image. And of course, the face space is where we will be doing the classification. So the closest faces to this new face that we get are going to take the name. So compare the projections onto face space to recognize the faces. The steps are pretty basic. Get the images, calculate the eigenbases, get the new image, project it into the face space, and report the image if it's known face. If it's a known face, basically do the facial recognition. Special case, if it's an unknown face and you want to add it, in this case, you need to calculate the step 2 for all images again. What does this mean? If you get, let's say, a point in here, if it has like lots of neighbors around it and they are of the same person, we classify it. But if we get a point here and all the other points are here, so definitely this is a new person, right? So certainly you're going to require some sort of a thresholding mechanism. So they used for step 1, they used a database of faces called AT&T from AT&T, and the dataset statistics are all in grayscale. Image sizes are 92 times 120, and we have 10 images of each person, and we have 40 people in general, so we have 400 images. Note these 10 images vary in terms of lighting, facial expressions, and facial details. Of course, some of them with glasses, some of them were not, some of them are rotated, some of them are not, some of them are smiling, some of them are sad, some of them are stuff like that. How do you calculate the eigenfaces? Again, if you remember how do you do PCA, this should be pretty easy. Simply, we're going to convert or flatten every single image into a single vector, a one-dimensional vector, as we discussed. And then this one-dimensional vector, we will combine all of them. Basically, we have features and what are they called? Features and columns, right? From here, we will get our average face, which is just the like the summation of every face divided by the number of faces, which is 400, as I remember. Yeah, 40 times 10, 400. And then what we do is we calculate the eigenfaces. So remember what we do is we take the faces, normalize our data set. So we get this adjusted faces data set. And from here, we calculate the covariance matrix. This is a very difficult or intractable task to do. What we do is we calculate the opposite direction. So instead of doing 1,300 to 400, so 10,000 by 400, we do the opposite, 400 by 10,000. And we get a much smaller 400 by 400 covariance matrix. And we compute the PCA to get the eigenvectors for these for this one, right? So instead of having 400 vectors, now we're going to have only a few of them that we decide, right? This process right now should be pretty similar, right, to PCA. Remember, we get this beautiful matrix. The first few eigenvectors are the most important. The last ones are going to be the least important. And of course, we get a beautiful one like this, which contains the eigenvalues in this region. And you can, using these eigenvalues, you can sort the eigenvectors that you want. But for us, what we care about is, of course, how many of these eigenvalues will we take. This is a like hyper parameter that you can play with PCA. Once you have that, the last step, once you have this face eigenfaces and you have the projection into PCA, you can easily take a new face and project it into the face feature space or the face space. And from here, compare each one with what you have, right? So the face recognition test, this is the test image, let's say G, is projected into the face space where we have all of our beautiful spaces, hopefully closer together, because we are using like this, right? And like we hope or we assume that the faces of the same person should be clustered together, right? This is our hope because they're of the same person, the same class, they should be closer together by PCA. And what we simply do, we calculate the distance to each face. The class is defined by, so the distance between, or the, what is it called? Euclidean distance between the new faces and every single face, and the threshold is set for the facial recognition. So if the distance is bigger than, let's say, 10, this is an unknown face. If the distance or the closest person is smaller than 10, then we take this person as a known person and we give it its name. If you would like to see some more complicated algorithms, you can take a look at DeepFace or FaceNet. FaceNet, we will not cover it in this course, but we'll certainly cover it in more advanced courses about advanced computer vision. We still have some time if you guys have some questions. So again, what we have covered in today's course is facial detection using Viola-Jones algorithm, which is a very simple algorithm, as we said. It uses these HAR-like features to detect faces. We saw that these HAR-like features there are lots of them. So in order to choose which part or which subset of these HAR-like features and which sizes should we use, we simply train a boosting algorithm. So basically we combine a couple of these weak learners and see if they give us a strong learner. If they do, of course, this training process takes a lot of time. We take the best one, the best combination that we have. We saw that it gives a 100% detection rate. So it detects all the faces, but it has a high false positive rate. So what we do is we use this attentional cascading, meaning we take, we try with two features, see if it's a face or not. If it's not a face, we reject it. If it's true or predicted as true, we doubt it. So we take it into a more complicated model. If it says it's true, then we doubt it again and take it to a more complicated model. If it stays false, we stop. If it says true, we doubt it again and give it to a more complicated model and repeat this process again and again in order to remove as many of these false positives as possible. And then we saw that the facial recognition technique is pretty simple, and it relies on taking the faces into a PCA space or a face space using the eigenfaces technique. And from there, we just combine compare the distance between the faces that we have and the new face that we get. Again, the computation is pretty similar to what we have studied already, simply by using a small distance, Euclidean distance, and a threshold on the face. Does anybody have any questions about Viola-Jones or eigenfaces algorithm? Or PCA, maybe, or ADA boosting? Nope. If not, then thank you so much for attending the lecture. With the Karam, you're gonna see a lot more about Viola-Jones algorithm. You will see how you can use it. Probably you're gonna see how you can use it in OpenCV. You will see how to download these pre-trained HAR-like features and download the ADA boosting classifier weights, and of course build your own classifier. And this technique has been used for detecting faces, detecting chairs, detecting animals and stuff like that. So it's not just for faces, it's just for object detection in general, but it works well, it works the best for faces. So thanks a lot and good luck with Karam. If you still have any questions, please always feel free to ask me or contact me directly. And remember, this is not like the best facial recognition software out there. It's just the fastest for development, and it takes less computations, right? If you want to do very accurate facial detection and facial recognition, you should use neural networks because they are much better, but they do require a lot of GPU and a lot of memory. So thanks a lot, and see you on Monday.
Thank you. Goodbye.
There will be a quiz on Monday too. Thank you.